Okay, in this video I'm going to do a quick review of local, global, and absolute mins and maxes. And then we're going to apply all of those to this problem down here at the bottom. So remember, a local min and max is basically any peak or valley of a function, and those peaks can be smooth or they can be pointy. And we find local mins and maxes by finding critical points using our first derivative and then using our first or second derivative test to find whether they're a minimum or a maximum. So let's go ahead and do that with our function down here. F of x equals 3x times x plus 4 to the 2/3. I'm not going to worry about this on the interval 5, 1 because that's only going to come into play when we're talking about absolute. Okay, all right, so first thing we need to do is take a derivative. Notice that again, this is a product rule. I have 3x times x plus 4 to the 2/3. So I'm going to do product rule. Product rule says derivative of the first, 3 times the second, x plus 4 to the 2/3, plus the first, 3x, times the derivative of the second, 2/3, times x plus 4, 2/3, excuse me, minus 1/3, excuse me, 2/3 minus 1 is negative 1/3. All right, let's do a little simplification. Three and 2/3, the 3's cancel, leaving me just with 2x. And then I still have that x plus 4 to the negative 1/3. A weird factoring technique is going to come into play again. Each of these have an x plus 4 in them. I'm going to pull out the lowest factor of x plus 4 that I have. In that case, that's x plus 4 to the negative 1/3. That's going to leave me with 3 times, remember, when we divide x plus 4 to the 2/3 by x plus 4 to the negative 1/3, which is what we're doing when we're factoring out, we're really taking exponent, 2/3, minus exponent, negative 1/3. 2/3 minus negative 1/3 is 2/3 plus 1/3, but 2/3 plus 1/3 is 3/3, or just 1. So 3x plus 4 to the 2/3, when I pull out an x plus 4 to the negative 1/3, is 3 times x plus 4, plus 2x, and I pulled out the x plus 4 to the 1/3. Distributing the 3 gives me 3x plus 12 plus 2x. 3x plus 2 is 5x. 3 times 4 is 12. One last step, I'm going to write our derivative just by moving that x plus 4 to the negative 1/3 into the denominator. X plus 4 to the 1/3, or cube root of x plus 4, either is fine. Okay, so here's our derivative. Our derivative gives us our critical points. Critical points come either when the derivative is 0 or when the derivative is undefined. Our derivative is going to be 0 when our numerator is 0. So f prime equals 0 means that 5x plus 12 equals 0. Moving my 12 over gives me 5x equals negative 12. Dividing by 5 gives me a critical value at x equals negative 12 fifths. Okay. The second place we get critical values is when our derivative is undefined. Our derivative is going to be undefined when our denominator equals 0. Solving this, cubing both sides gives me x plus 4 equals 0. Subtracting 4 gives me my second critical value at x equals negative 4. All right, so we have two critical values and we have our derivative. I'm going to rewrite our derivative down here so we don't lose it because we might want it later. Okay, and then our critical values are x to the negative 12 fifths and x equals 4. So I'm going to pause it. Okay, so again, here's our critical values. So to classify our critical values, which is part of finding local mins and maxes, I'm going to go ahead and do the first derivative test. Technically, I could do the first or the second derivative test. Second derivative test would involve taking a derivative of that. We don't really want to find the second derivative, so let's just do our first derivative test. So I'm going to put in my critical values, -4 and -12/5. I like to remind myself what that means. So at -4, f prime was undefined. At -12/5, f prime was 0. All right, so let's pick some test values and see what we get. All right, so over here, let's pick, say, -5. I'm taking -5 and I'm plugging it into my derivative. Now I'm just going to do this using signs. When I plug -5 into my derivative, 5 times -5 is -25. -25 plus 12 is still a negative. So I've got negative on top. Plugging -5 into the bottom, -5 plus 4 is -1. Cube root of -1 is still negative. So I've got negative divided by negative. That overall means my derivative, f prime, is going to be positive, which means my function is increasing. Now let's pick something between -4 and -12/5. -12/5 is 2 and 2/5. So -3 is going to be between those two. Again, I'm going to play that positive and negative game. Plugging -3 into my derivative. 5 times -3 is -15. -15 plus 12 is still a negative number. Plugging -3 in down here. -3 plus 4 is +1. Cube root of +1 is positive. Negative divided by positive is a negative. So my derivative is 0, or sorry, my derivative is less than 0, a negative, meaning my function is decreasing. That tells me right here that this, increasing to decreasing, is going to be a local max. Okay, now picking something over here, I like to pick easy values like, hey, 0. When I plug 0 in to the derivative, I'll get 12, which is positive, over the cube root of 4, which is a weird number, but it's positive. Positive divided by positive means my derivative is positive, so I'm increasing. Okay, so one thing this actually lets us do is sketch a little picture of the shape of our graph. Now I'm increasing to decreasing, increasing to decreasing. That means that I'm a max, but because I'm undefined here, not only am I going to be a max, I'm going to be a pointy max. And then I'm decreasing to increasing. Decreasing to increasing means that -12/5 is a local min. And because f prime is 0 there, it's going to be one of those smooth mins. So I've got a pointy max and a smooth min. Okay. All right. So, whoops, I don't know why I just put another random min in there. This is still going to be increasing for the rest of the graph, like so. Okay, so a couple of things that this tells us. We've looked at our local min and our local max. We found that this function has both a local max and a local min. Now let's talk a little bit about global mins and maxes. Remember that when we're looking globally, we're looking at the entire domain of the function. So I want to think, okay, does this function take on a biggest value and a smallest value? And we saw, just with our use of pictures, that some functions have a global max and no global min. Some have a global min and a global max. Some have a global max but no global min. And some have neither a global max nor a global min. And our little graph here not only tells us kind of the basic shape of the function, but can also tell us whether or not this function has a global max or a global min. So if I'm thinking global max, I notice that, over here, our function is going to keep increasing forever. I mean, it's going to keep getting bigger and bigger and bigger. That means our function has no global max. Similarly, over on this side, the reason why I was upset with myself for kind of putting in a random upturn there, on this side, our function is going to keep decreasing forever and ever and ever, meaning our function also has no global min. What a bummer. All right, well, real quick, it's nice to sometimes check our work. So I'm going to go ahead and pull up this graph on Desmos. So there's our function, 3x times x plus 4 to the 2/3. And then let's look. I'm going to zoom out a little bit. Okay, maybe. All right, so there certainly is our global max at -4, or local max, excuse me, bad use of terminology, our local max at -4, and it certainly is a point Emax. And there is our local min at -12/5 or -2.4, and it is a nice smooth rounded local min. And it sure looks like this function is going to continue forever and never have a global max, and continue decreasing forever to never have a global min. So our graph here matches what we saw on our board up there. So that's really great. All right, I'm going to pause for a minute, erase the board, and then we're going to talk about absolute mins and maxes. Okay, so we've talked a little bit about local and global mins and maxes. Now let's talk about absolute mins and maxes. Remember, with an absolute min and max, it's like we're zooming in on a function between these two values. And in particular, the values that we want should be -5 to -1. Otherwise, that interval doesn't make very much sense, does it? The interval that we care about is -5 to -1. So if you imagine that graph that we looked at before, we're zooming in between -5 to -1. It's like the rest of the graph doesn't exist. Okay, so to find absolute mins and maxes, remember what we do. We find our critical values of the function. Well, luckily, we've already done this. Here's our critical values. X equals -12/5, and x equals -4. Okay? We're going to look at the critical values and the endpoints. Okay? And in particular, we're going to say, hey, which of these critical values falls within this interval? Well, between -5 and -4, between -5 and -1 is -4. And between -5 and -1 is -12/5. In this case, both of our critical values fall within the interval that we care about, -5 to -1. So we're going to include both of them in our next calculation. So we're going to check the critical values contained in the endpoint. Contained in the interval. In this case, that's both -12/5 and -4. Sometimes it isn't. And the endpoints of the interval. So in this case, that's -5 and -1. We're going to check those by plugging them into the function and seeing which gives us the largest value and which gives us the smallest value. So I'm going to take all of those and plug them into our original function. Okay, now this means I'm taking this and plugging all of that into this function, 3x times x plus 4 to the 2/3. Now, because that is a lot of stuff to plug in, I'm going to go ahead and work smarter, not harder, and I'm going to use Desmos to do this calculation for us. So the first thing I want to know is f of -5, which Desmos handily tells me is -15. And then I want to know f of -4, that's one of our critical points, which Desmos tells me is 0. And then I want to know f of -12/5, which Desmos tells me is -9.85. And then I want to know f of -1, which Desmos tells me is -6.24. Okay, so now we have values for all of these. So let's go ahead and pick out which is our absolute min and which is our absolute max on the interval -5, -1. When I'm looking for my absolute min, I'm looking for the smallest value. Well, the smallest value is -15. So this is going to be our absolute min on that interval, -5 to -1. Biggest value is our 0, and that's going to be our absolute max on -5, -1. Okay, so when we're finding absolute mins and maxes, we have to test all critical points points that are contained within our interval, and also the endpoints of our interval. In this case, one of our critical points gives us the absolute max, but it's on the endpoint, -5, that our function actually receives its absolute min.